Hello everybody, today we're going to be discussing chapters 3.1, 3.2, and 3.3. That's equilibrium, free body diagram, and then coplanar force systems. So let's talk a little bit about equilibrium. I have a table with a book on top of it here, and I'm saying that it is equilibrium, meaning that the force of the book is not moving the table. So I could say that if I sum my forces in the y, they are equal to 0. Also, I could say that if I sum my forces in the x, it's also 0. And these are our equilibrium equations. So let's come in and say I've got some type of object, and I have these forces acting on this object, whether it's 3 people pushing on a ball or something, and everything is in equilibrium. Well, then I could say that this is force 1, this is force 2, and this is force 3. Let's draw a quick axis on this. So we could say this is my x and this is my y. If I said that this was theta and this is alpha, then I can come in and say that if I sum all my forces in the x is equal to 0, it's in equilibrium, meaning that the force of 1, so force of 1 is acting in a negative direction, in a negative x. You can see that going this way. It's a negative x. It's a negative f1, and that would be cosine of theta. F2 is also going in the negative direction, but this is going to be sine. Notice that, remember, this would be opposite, so this would be alpha. It's going to be minus f2 sine alpha. And then f3 is in the positive direction, so we're saying plus f3. All of this is equal to 0. If I sum my forces in the y here, then it's just going to be f1, which is a negative f1 because it is going down, times the sine of theta, plus f2 times the cosine of alpha is all equal to 0. Now we don't need to worry about f3 because it is just in the x direction and it's not causing any other action in the y direction on this object. So these are your equilibrium equations when we're talking about a two-dimensional object. Okay, so I've got a weight hanging from an O-ring, and it's attached by 2 cables. And we can say that maybe they're not exactly level. So you could say maybe that's, I don't know, a couple inches or something off. And then we could say that this point here is point A, B, and this is point C. So the first thing you're going to want to do in any one of these problems is draw the free body diagram. So if we're looking at the free body diagram, the first thing we're going to do is the free body diagram of the weight. So when I have my free body diagram of the weight, I have the mass times gravity. So if they're giving it just in mass, let's say they gave us 20 kilograms, and you would multiply that by 9.81 meters per second squared. And then you would also have, if we call this B, and let's say we could call this D, this point D, this would be tension of dB. That's the tension coming off of here. So if we looked at the object B here, if we have our ring here, we're going to have these tensions, and then notice how I draw tension dB here, dB there. It's opposite of what it is on the weight. So this is the same. These are the same in magnitude, but on the object itself it's just going to be in the opposite direction. So this would be TBC, and this would be TAB. And then you would sum your forces again, sum your forces in the x, and you would sum your forces in the y. And you would use your angles that were given to you, and you could solve for the tensions in AB and BC using these 2 equations. We're going to get into some examples here in a little bit. Thanks for listening.